Hi, everybody. We are going to be learning today about something known as stellar evolution. It's the life and the death of a star from the time they were born until the time they fizzle out in the sky. Now, there are many things about stars that we know because we study them in their different life stages. We are not alive long enough to watch a star form, go through all the phases, and then fizzle out. So, as I'm about ready to begin this discussion, you should be following along with your notes, which is a table that I created where you're going to be filling in the blanks as we go. So, we're going to be looking a lot at the stellar life cycle over the next week. This life cycle is a flow chart showing you from the very beginning, right here, what happens to stars depending on how much matter there is to begin with, whether they take this top path here, whether they go the bottom path here. And then you can see that complex things that can happen. Arrows are going one way and another way. So we will be dissecting them from their birth until they become sometimes remnants. There are a bunch of different ways to look at that diagram. This picture shows you actual images of the stars from the time that they begin as a nebula, going through maybe their low mass or a high mass portion. So we're going to be looking at all of these different components today and dissecting the details of that. Here's another way to look at stars from the time they're beginning until the time they end. So you're going to see a bunch of different diagrams on how this works from stars being born until they end. So the first phase in a star's quote unquote life is when a star begins as a nebula. Nebulas are where stars are born. And in the box that says composition, you should definitely include that a nebula is just gas and dust. The gas and dust is composed mostly of hydrogen. 70% of it is hydrogen. 28% of that gas and dust is helium. 2% of heavier elements that we'll talk about in a little bit. What is the energy source for all this gas and dust? The energy source is simply gravity. Gravity is pulling all of that gas and dust together. And how long does it spend in this little stellar nursery called a nebula? Several million years it takes for gravity to overcome those forces and pull together that gas and dust to create a star. So I'm going to show you a bunch of images right now. They are all real and they are taken with the Hubble Space Telescope. This first image is a nebula called the Crab Nebula, and you can see all of the different colors within this, the yellows and the reds and the white. Just so you know, the Hubble Space Telescope was launched in 1990 and it does not take color images. All of the images transmitted back to Earth are in black and white. So NASA has to take the spectroscopy and then color code the different temperature regions, which we've already done in this image to create what you see. So the image shape itself is real. The color has been enhanced after they received the transmission. So this is one nebula called the Crab Nebula. This one's called the Cone Nebula. And you can see the gas and dust is very evident in this photo. This is called the Horsehead Nebula. As you can see, it got its name from this horse head-like shape. And if we zoom out, looking at that same nebula, there it is right here. So you can see the great vast amounts of gas and dust in space. Remember that each of these dots that you see, whether they're bright or whether they're really tiny, they're stars. Some stars closer, maybe they're bigger, some stars brighter than others. So imagine how big this nebula is if you know that 90% of the stars in that image are the same as the sun. Imagine how big these stellar nurseries really are. The Eagle Nebula is another famous stellar nursery where stars are born. And within this, you can see little bright dots of stars being born. All right, other stars around it in the foreground. Let's zoom in on the Eagle Nebula. And there's a really amazing photo taken by the Hubble of a gas cloud where stars are born. So these nebulas spend millions of years contracting due to the forces of gravity to start beginning a star. Now, the second thing that happens is finally enough gravity overcomes the dust and gas, and the center of that star starts to shrink and spin, and we start to get the beginnings of a star. So, what is a protostar's composition? Mostly hydrogen and helium, and a plasma becomes formed due to the superheat, where the electrons become stripped off the atom. What is the energy source for a protostar? The energy source is collisions of particles. So there's a lot of friction and pressure going on. So again, these keywords in blue are the words you want to be putting on your notes guide. So the temperature starts to increase rapidly as friction and pressure start overcoming the particles. How long is it going to stay a protostar? Several million more years. So it stays a protostar, which is not officially a star, it's like a prototype until fusion begins. So it'll stay in this phase until nuclear fusion begins. So we have a few images of protostars from studying these gas clouds. You can see right here, do you see how the gas and dust is illuminated? So it's beginning to form a star. Right here, you can see another protostar in the center of that gas cloud, and another one actually starting fusion right there. Now, once nuclear fusion begins, a protostar becomes a star when the fusion reaches a temperature of 10 million degrees Celsius. You should jot that down on your notes where it says main sequence star on the left-hand side. A star is not a star officially until it hits 10 million degrees Celsius. So what is the main sequence star composed of? Hydrogen and helium. What is the energy source? Nuclear fusion. Notice though, it's not just plain, there's plenty of types of nuclear fusion. This fusion is hydrogen to helium fusion. All right, that's really important that you write that down for the main sequence star. So in this phase, a star is considered stable. It is a stable size. And the reason we consider it stable is this is the longest stage of a star's life. Stars will spend anywhere from several million to 10 billion years in this main sequence phase because there's a lot of hydrogen to burn into helium. So this is the sun. It's a real image of the sun taken by a satellite called the Solar Dynamics Observatory, where it can zoom in on these solar prominence as you see. So you're looking at a gas ball, a plasma ball of hydrogen and helium blowing up and held together by gravity. Vega is another star that's out there in our galaxy, main sequence. Even though it's blue, as you can see right there, Vega and the sun are main sequence stars. Look at this picture. In fact, now that you know about your HR diagram, you know that 90% of the stars in that image are main sequence. The size and temperature of the star determines its path next. So we could either go one of two routes. A star that begins off in a very large stellar nursery of gas and dust, think of like a large baby, will end up becoming a supergiant. But a smaller cloud of gas and dust becomes a giant. But the characteristics of both are similar, it's just the size that differs. So we're going to go ahead and write this information in the same box for giant and supergiant. So what are these two mammoth stars composed of? Hydrogen atoms are all gone and now they fuse to helium. So the main ingredient in the giant and the supergiant is helium. What is the energy source? Well, the energy source is the helium to carbon fusion this time because the core of the star begins to contract and increases the temperature. So now what you have is this helium that's left over from all of the hydrogen that was used up, and it starts fusing into heavier elements like carbon. So what happens, why do these stars get so big? Well, their outer shells start to expand greatly. And if you compare these stars to the sun, these giants and supergiants are up to 8 times more massive. That's crazy. How long do they spend in this phase? Only a few thousand to a billion years. In the grand scheme of the age of our universe, that's actually really, really short. So they're not going to stay here very long once they start swelling and becoming more massive. So there's a few pictures. This one's a drawing, not a real image, but it shows you the inside of a red giant is fusing helium. It's burning helium and fusing into heavier elements like carbon or oxygen. And the shell starts to cool. That's why these are really cool temperatures and swell, becoming really, really big. So Betelgeuse, here's the constellation Orion. Betelgeuse is a supergiant star. You can actually see with the naked eye its red color from Earth. And it's very far away, yet it's one of the brightest stars in our winter sky. So that tells you how big and bright this is. But it won't be there forever. Betelgeuse is in its dying phase as it starts to swell. If you imagine how big is Betelgeuse, if Betelgeuse was the center of our solar system, everybody, it would swallow all of the planets, including Saturn's orbit, all the way out to Uranus. So this is a picture of Betelgeuse from the Hubble Space Telescope. And it shows you that our solar system would begin right here with the orbit of Uranus, and everything else would be swallowed up. This is a really creepy artist rendition of what it would look like if Betelgeuse was our sun superimposed over the city of Seattle. That would be really crazy, and seeing that in our sky instead of our sun. Right now, from the supergiant and giant phase, if the star doesn't have enough gas and dust and it took that giant path where it was a smaller baby in the beginning, those stars will become something known as a planetary nebulae. Their main composition is carbon, so write that down. And what is the source of energy? The source of energy is none. These stars are losing all of those outer gases, revealing a simple core. All right. So the expanding gases is what produces whatever leftover there is of energy. And how long does it spend as a planetary nebula? Only about 10,000 years. Now, these are some of my favorite images from the galaxy, from the Hubble Space Telescope. Planetary nebulae can look like this. There's 6 different varieties of them: the Eskimo Nebula, the Ring Nebula, the Necklace Nebula, the Spirograph. I love the Cat's Eye, that's one of my favorites, and the Hourglass Nebula. So you can see at the center of all of these, you see that little dot? That is what's left, going to be left over. So these were only giant stars. They couldn't be super giants, right? They didn't have enough matter. So giant stars that start to die off, once all those heavy elements get burned away, you're left with just the core. But as they're dying, they are beautiful. All right. This is the Cat's Eye Nebula up close. And if you look very carefully at the center, you see what's going to end up being left over. As all of these gases escape, they become really pretty as they die. What do they turn into? Well, smaller main sequence stars will end up as white dwarfs. These white dwarf stars are really just composed of hot, dense cores of carbon. It's that little dot in the center of that planetary nebula that's left over. So gravity causes the star to collapse. This occurs when helium fusion of a red giant ends, and it's got to be only a medium-sized star to a small star. What is the energy source for the white dwarf? There is no energy source for fusion. They were held together by electron pressure, and that's it. So it's a very unstable stage. How long will it stay a white dwarf? Billions of years as it cools off and becomes fainter and fainter in our sky. Now, some scientists say it may become something known as a black dwarf because, according to the laws of nature, matter cannot be created nor destroyed. So they're saying if there was matter in the star that's starting to, fizzle out and burn away, you can't destroy it. So it must be out there in space. And they say that that's what a black dwarf might be. Now, do we have pictures of white dwarfs? We do. Look at this. This is a little bit of a planetary nebula left over, but you can see the white dwarf right there. Now, these are very tiny. In fact, so tiny with the naked eye, we do not see them from Earth. These big bright things are main sequence stars. This picture was taken by the Hubble Space Telescope. But wherever you see these little white circles, that's a drawing circling where the white dwarfs would be. So we don't see these from Earth, but they are out there. These tiny little white dwarfs. They're hot, they're blue, and they're dying. Now, sometimes as these white dwarfs are starting to cool off, they explode. And we call those little explosions novas. Novas, what's the composition? Just gas and dust from these binary stars. And sometimes they cool, they explode several times, not just once. What's the source of energy? Gravity. And can we see this from Earth? Even though it's 1,000 times brighter than the sun, we would probably need a telescope to see these novas because we can't even see the white dwarfs to begin with. Although there are 50 seen per year in the Milky Way galaxy, those are typically with telescopes or the Hubble. Now, how long do these novas last? Oh, they last a few days to maybe a week. And do we have images of these novas? We do. There is a picture of 2 white dwarfs that orbited each other. This one exploded. You can see all of the matter right here, but in a matter of a few days to a week, all this matter might collect back and make the star again, and then it could do that again. So they start contracting as they explode. This is another picture of a nova, and you can see the white dwarf in the center sending matter in all directions as it explodes. But what happens when a bigger star explodes? A bigger star such as Betelgeuse, a star that in that stellar nursery back at the beginning of this discussion was a really big baby full of gas and dust. All right. If there's enough gas and dust in the beginning to create a super giant will explode and it's called a supernova. So that's what happens when there is enough matter for carbon to fuse into an even heavier element known as iron. So jot down iron for the composition. What is the energy source in a supernova? Well, because there's no electron pressure, the star violently collapses in on itself and explodes. So it's like 1 million times the mass of Earth collapsing into 15 seconds. Now, this explosion will look as bright as an entire galaxy. And how long do these explosions last? They last sometimes a few weeks up to months. These explosions are definitely seen with the naked eye if you know where to look. They enrich the universe with new elements, and they're not very common. There might be 2 to 3 of these per century. The last one was directly observed in the year 1604 by Johannes Kepler, who's a famous astronomer. So, what we study today are the remnants, the leftovers of these explosions. So, let's check out a few pictures of supernova. This is one that we can actually see the leftovers of. Right here, that's a picture of the supernova from far away. And if you look up close, you can see how big this is. These bright dots right here are main sequence stars in the foreground. So that's how big this explosion is. There's that same explosion from very far away. So if you knew where to look in the night sky, you would see that explosion in between the main sequence stars right there. Now, this is the last one that was observed by the naked eye. Kepler marked it right here. You can actually see that this photo was taken by the Chandra-Ray Observatory in 2013. So this is the remnant right there in this constellation that was taken by this observatory that was actually able to scan space and find those remnants. This is another supernova that happened in 2006. It was the biggest one ever recorded. It occurred in a galaxy 240 million light years away, and it was 100 times more energetic than any supernova. Again, the Chandra X-ray Observatory could see this with X-ray technology. That's the explosion, and that's an artist's rendition of a supergiant blowing apart. Now, what happens after a supergiant explodes into a supernova? Well, there are 1 or 2 things that could happen. If there's enough material left over, that iron will come back together and form a very, very dense ball of neutrons of iron. So that's the composition of a neutron star. In fact, some scientists estimate that a spoonful of matter from a neutron star could weigh up to 100 million tons on Earth. Now, what is the energy in these neutron stars? The contraction of iron. The iron is contracting in the core and it starts spinning really, really rapidly. The diameter of these neutron stars is only about 20 kilometers. That's the distance from here to Detroit, Wyandotte to Detroit. Neutron stars sometimes start spinning so rapidly as they're contracting that they give off beams of radiation or radio waves. So we call that a pulsar. In other words, it looks like a giant lighthouse sweeping out into outer space. How long will it spend as a neutron star? The rest of its life. So this picture right here is showing a neutron star in this gas cloud right here. You can see the light beams. And really, they're very slow rotating. Most of them are only detected if they have the pulsars and they're rotating very rapidly. Otherwise, sometimes you can't even see them. This is just a drawing showing you the mass of a neutron star. If you compare it to Earth or our sun, you can see it is insanely massive. And this is a picture of what happens when the core of a neutron star starts to contract and spin rapidly. It creates these energy beams we can detect by looking for radio waves, and that's how the neutron stars are located. These, again, are called pulsars. Now, what happens if there's not enough matter left over after a supernova explodes? It becomes one of the most mysterious things in outer space, or a black hole. So, a black hole forms when a massive supernova cannot form a neutron star. So, what is a black hole made of? Incredibly dense matter. And the force of contraction of that matter crushes the core of the star and leaves a hole in space. So, what's the energy source for a black hole? Gravity. They say the gravity in a black hole is so great that not even light can escape. So, how do we find them if they're black? Well, the answer is we look at their effects on companion stars nearby, and sometimes they pull light in. And as light gets sucked into the black hole, it gives off an X ray and you can locate it. So, how long does it spend as a black hole? Well, the time is very, very unknown. So we have images of black holes. In fact, one was just imaged last year. But this is a black hole in the Cygnus constellation right here. And you can see where light is being pulled in. It shows up in outer space. We can see another image of a black hole here and a bunch of images, right? These are gigantic. But to really understand how they're located, I have to show you this drawing. The black hole, sometimes if there's a companion star nearby, the black hole will start slowly sucking matter in. And as the light gets sucked in, it gives off X rays that we can see. And so it doesn't swallow up the whole star. It's not like a vacuum cleaner sucking up things in space. It just slowly pulls matter in over time. So this is an artist rendition. This is not a real photograph of one. And there's another artist rendition showing how light cannot even escape these black holes. So, what else could happen out there? Well, sometimes, you guys, stars are massive enough to only fuse elements known as deuterium. So, deuterium, if we compared it to like the mass of the sun, this is 0.08 the mass of the sun. So, these brown dwarfs out there are made of an isotope of hydrogen. We'll talk about isotopes later, called deuterium. And sometimes we call these brown dwarfs failed stars, and they spend the rest of their life in this phase. So that's a little bit about a brown dwarf. Stars massive enough to only fuse the element deuterium. So if you look at the size of a brown dwarf, it fits right here between Jupiter and maybe a low mass star. So that's where the brown dwarfs are, and there's Earth for scale. There's also a star known as a red dwarf. You graphed many of these red dwarfs on your HR diagram. These are stars large enough to fuse hydrogen into helium, but their masses are still zero point 0.5 of the sun. So they are made of hydrogen, and they do make up 70% of all stars that we see in our galaxy. They are part of the main sequence. When you were plotting the red dots with Cami on your HR diagram, most of your stars were red dwarfs. They spend trillions of years in this stage here. So this is just a picture just showing you cooler stars, stars like our sun, and hotter stars. You're going to find these red dwarfs right here. 70% of all stars are right in this section here. How many red dwarfs are there? If you looked at the percentage of main sequence stars in the universe, if you look, and we had to graph it all out with, this is how many would be red dwarfs. And then the rest of the stars would be over here. And that's main sequence. So our sun falls in this section right here. It is definitely not a red dwarf. So these are pictures of red dwarf stars, comparing them to brown dwarf stars and the planet Jupiter, and then our sun over here. Just to give you guys scale on how big these red dwarf stars are. So there's Gliese, and then these are brown dwarfs here, and then Jupiter.